Okay, so this is theorem 13.9, and I really view it as a kind of special case of this theorem 13.8, when instead of having a monic here, we just have a general arrow, and the result is basically the same. So we have that for a relation R on B times A, and for an arrow W from zeta to B. I'm sort of flip-flopping between using zeta and capital S for this object because I in the book it says S, but I sometimes prefer to write zeta because it's easier to distinguish between that and the lowercase s. Anyway, the result is that W is in for all AR if and only if W times 1A is contained in R. So the proof is basically the same. W is in for all AR. Well, for all AR is just the inverse image of the name of T under the transpose of the classifying arrow of R. So this is equivalent to saying X is in that, which is equivalent to saying that doing the transpose of the classifying arrow on W is in the name of T, which is equivalent to saying that that's equal to T exclamation mark zeta. Doing the transpose of this, we get that, sorry, I keep calling this zeta as well, this is chi. Sorry, no, that's equivalent to saying that chi r of W times 1A is equal to T after exclamation mark zeta times A. That's just doing a transpose using that exercise from the exponential objects Cartesian closed category section exercise. And then this is equivalent saying that W times 1 is in R, just by the subobject classifier thing. And then notice that this is actually a graph, so it's a monic. So we can write this is W times 1 contained in R, for what difference it makes. Now, a corollary to this is that W is in for all AR if and only if for any C with arrows H into S and K into A, we have WH comma K in R. And we can see that because this condition B here is equivalent to W times 1A is in R. We can see that because if W times 1A is in R, well then that just means that WP1 comma P2 is in R, which means that there exists a K such that WP1 comma P2 is in RK, which means that there exists a K such that WP1 comma P2 after HK is equal to RK after HK. Oh, we shouldn't use K there. Let's use a squiggly one instead. K squiggly, K squiggly, K squiggly, K squiggly. Now the top, this part here, like before the equal sign, that's just WH comma K, and then clearly that's in R. So we've got A implies B, and B implies, well, we've got that this W times 1A is in R, implies this, and then this clearly implies this, because we can just set H equal to P1 and K equal to P2, and we get this directly, and this is equivalent by the last theorem to saying that W is in for all AR, so that does it. Next result then, theorem 13.10. This is a bit of a challenge, I think, if I remember correctly. So for, actually, is this a challenge? Yeah, this is the last big result of the chapter. So let's get the statement correct for a start. So I believe there's a bit of a typo there. I think they just mean that R is a subobject of A in this case. Let's just make a note of that. R. I think that's what they must mean, otherwise. Yeah. So anyway, we've got these subobjects R and Q of A and an arrow W into A. Now the claim is that if we let Y be defined by this pullback square, so Y is the pullback of Q along W, then we've got that W is in Q double arrow R, if and only if WY is in R. I quite like this proof because it sheds a lot of light for me on what Q double arrow R is, although I must admit I still have to really internalize the sort of meaning of this theorem in some sense, although I can prove it. So this is all my personal attempt. Now let's get on to the thing. So what's the situation? Well, it basically looks like this, okay? We have this sort of implies arrow being the classifying arrow of less than or equal to 1. And then we have that this Q and double arrow R thing is the subobject classified by little arrow after chi q comma chi r, and we have this y here, which is the pullback of q over w, and we're asked to show that w is in q double arrow r if and only if wy is in r. Okay, so firstly, notice that wy is qi because they say we have this pullback, so that means that wy is in q. Now we're going to start by showing that this implies this. So we'll suppose that w is in q double arrow r. Well then, there exists a k such that w is equal to q double arrow rk. So wy is q double arrow rky. So wy is in q double arrow r. And we also know that wy is in q, so wy is in q double arrow r intersection q. Now, using theorem 13.6, which says this, when S squiggle is q double arrow r, we get q double arrow r is containing q double arrow r is automatically true. And so we automatically get that q double arrow r intersection q is contained in r. So we know, since we know that wy is in q double arrow r intersection q, we know now that wy is in r, which is one of the ways around we want to do. Now the other way. Suppose that wy is in r. Now, since y is just another name for the pullback of q along w, we can write y is equal to w to the minus 1q. And we have that w to the minus 1q, which is y, is contained in w to the minus 1r. And an implication of that is that we have that w to the minus 1 of q is equivalent to w to the minus 1 of q intersection r. And to see that, we can just do a kind of member-based argument. So m is in w to the minus 1q implies m is in w to the minus 1r by this. And so wm is in q and wm is in r. So wm is in q intersection r. So m is in w to the minus 1 q intersection r. So we've gone from this to this. Conversely, suppose m is in w to the minus 1 q intersection r, then wm is in q. So w is in, so I should say m is in w to the minus 1 of q. All right. Well, we have to use everything for this result. Now, let's remember one of our previous results. Purple star, here it is. And that is that in general, we've got chi qs classifies s to the minus 1q, so classifying arrow of it. So we know then from that chi q of w classifies w to the minus 1q, and also that chi q in section rw classifies w to the minus 1q in section r, but these are equivalent monics, so their classifying arrows are the same. So we have chi q of w equals chi q in section r of w. And that means that w equalizes chi q and chi q in section r. Now that means that w is in the equalizer of chi q and chi q in section r. Now it turns out that that equalizer is precisely q double arrow r. Now we can see that using this red argument here. So for a general element, we've got mu is in q double arrow r is equivalent to saying that this is that little arrow, so we'll write it properly. It's chi of less than or equal to 1 after chi q comma chi r after m is true. That's the kind of this is a kind of sub-object based way of saying this. And now using the definition of sub-object classifier again, sort of changing, going from using this classifying arrow to talking about what's really going on, we have that this is equivalent to saying that chi q mu is less than or equal to chi r mu. Which is equivalent to saying that chi q mu is equal to chi q mu and chi r mu. But from our previous result about and, this is precisely the same thing as chi q in section r of mu. I showed that. Way up here, okay? So to summarize, we have from up here already that mu is in E. We already had this up here, that mu is in E is equivalent to saying that chi q mu equals chi q in section r mu. And now we have that, so mu is in E is equivalent to that kind of thing with mu's instead of thetas. And now we have that mu is in q double arrow r, precisely when exactly the same condition holds. So E has got to be equivalent to the monic q double arrow r, and we've already shown that w is in E, so w is in q double arrow r, and we're done. a corollary of this is that this, where is it now? So we've got W in Q double arrow R if and only if WY is in R. So we know that, but this right hand side we can express it in another way. So WY is in R. So WY is in R, which I'll call statement A, is equivalent to saying that for an arrow H from C to zeta, we have WH in Q implies WH in R. So given statement B, if we just set H is equal to Y, we immediately get, since we know that WY is in Q, we immediately get that WY is in R. So that's fine. Going the other way around, suppose statement A, and suppose WH is in Q. So if WH is in Q, then there must exist a K such that WH is equal to QK, which means the outer perimeter of this pullback square commutes, which means there exists a G such that, well, crucially, such that H is equal to YG. Now we're also assuming A, so we have that WY is in R. So there exists a D such that WY is in RD. So WYG is in RDG. Sorry, there exists a D such that WY is equal to RD. So WYG is equal to RDG. So, but H is equal to YG, so WYG is equal to WH is equal to RDG. So WH is in R. So we've shown that A is equivalent to B, and we know that A is equivalent to saying that W is in Q double arrow R. And we're done.